We clearly need to work through some examples that apply the concept of the sampling distribution of a proportion. And that is what we will do in this video. Here is our first example. Suppose that 13% of the population is left-handed. The school auditorium has 15 lefty seats. In a class of 90 students, what is the probability there will not be enough seats for the left-handed students? Now, 15 divided by 90 is 16.7%. So if more than 16.7% of the class is left-handed, there will not be enough seats. So a first step here was to recognize the need to convert 15 out of 90 to a percent. The problem states that the true proportion of left-handed people is 0.13, so that is our value for P. Q, which is equal to 1 minus P, is the proportion that are not left-handed, and that is 0.87. And finally, the sample size is 90. So we must check the success and failure condition to ensure that the sample size of 90 is sufficiently large to ensure that sample proportions will be normally distributed. And when we compute both NP and NQ, they are greater than 10, so we proceed to the next step. I suggest your next step is to calculate the standard deviation of the sampling distribution. If you recall, the standard deviation is given by the formula the square root of P times Q over N. And as this slide indicates, the standard deviation in this example is 0.035. Now remember the question. We need to find out how likely it is that in a group of 90 students, 0.167 or more are left-handed. So we draw a picture and we locate the true proportion of left-handed people, which is 0.13 at the center, and locate 0.167 to the right and shade above. Now remember how I told you that special z-score formula would be important. We need to convert the 0.167 into a z-score using the formula. P is the true proportion of left-handed people, and the standard deviation was something we just finished calculating. If you recall, that number was 0.035. So the z-score corresponding to 0.167 turns out to be 1.06. Next we go to our familiar standard normal calculator and determine that the area above z equals 1.06 is 0.144. So for the final and most important step, wrap up the problem and state your conclusion clearly in the context of the problem. There is about a 14.5% chance there will not be enough seats for left-handed students in this class of 90. Now let's turn our attention to another example. This one involves smoking. Public health statistics indicate that about 26.4% of all American adults smoke cigarettes. What is the probability that in a random sample of 50 adults, less than 22% smoke cigarettes? So we will follow the same procedure as the last example. We will check the success and failure condition. Next, we will calculate the standard deviation. Then draw a well-labeled normal curve and shade. Follow this up by calculating the needed z-score or scores. Use the standard normal calculator. And finally state our conclusion. So first we check the success and failure condition. Now I caution you to use the population proportion of smokers for P, which is 0.264, not the sample proportion mentioned in the problem. Q would then be 1 minus P. And if you examine the calculations carefully, you will see that both N times P and N times Q exceed 10, so we're all set. The calculation of the standard deviation is straightforward, provided you remember the formula and use the value of 0.264 for P. Don't forget to represent your problem on a normal curve centered in this case at 0.267. And since we want to determine the likelihood there will be less than 22% smokers in this group of 50 adults, we shade below 0.22. Next, use the sample proportion mentioned in the problem, namely 0.22, the population proportion, 0.264, and our recently computed standard deviation of 0.0623 to arrive at a z-score. And we find that negative 0.71 is the z-score that corresponds to 0.22. The standard normal calculator reports that 0.2389 is the shaded area below negative 0.71 on the standard normal curve. Don't forget to wrap it up. There is approximately a 24% chance that in a group of 50 adults, less than 22% are smokers. Notice our conclusion mentions the sample size, the studied population, namely adults, and the studied variable, namely the percent who smoke. For our next example, we consider a study that is looking at juvenile diabetes. Only 4% of children carry the gene for juvenile diabetes. The researchers need to follow 20 children who have this genetic gene. If they test 732 newborns for the gene, how likely is it they will have enough subjects for their study? So you know the drill now. Our first step is to verify the success and failure condition has been met. Our p-value is 0.04, the population proportion of children with the juvenile diabetes gene. Our q-value is 1 minus 0.04, or 0.96, the percent of children who do not have the diabetes gene, and N is 732. We calculate N times P and N times Q, and both yield numbers that are greater than 10. So the distribution of sample proportions of children with the gene for diabetes is normal, and we can proceed. Next, calculate the standard deviation as the square root of P times Q divided by N. We will need this number to calculate the z-score. We have not yet discussed the value of p hat. The researchers need at least 20 out of 732 to have the gene for diabetes. If we convert this to a fraction, they need 20 out of 732, which is decimally equivalent to 0.02725 to have the gene. The question then becomes, how likely is it that in a sample of 732 newborns, we will have at least 0.02725 or 2.725% with the diabetes gene? Since the issue is at least so many children, we shade above p hat. Next, we substitute the values of p hat, p, and the standard deviation into the z-score formula. The resulting z-score is a negative 1.76. Then we use the normal calculator to find the area above a z-score of negative 1.76. And the shaded area is found to be 0.9608. In the context of this study, we can conclude there is about a 96% chance that if the researchers test 732 infants for the diabetes gene, they will find at least 20 of these infants have the gene.